by today. So this is circuit with dependent sources, okay, for loop analysis. Basically, we have touched a little bit and like yesterday. So we treat every dependent source as if we're independent, so similar with the nodal analysis. But then we need the one equation for the controlling variable. So this is also the same with nodal analysis. Yeah, for example, like this one, we have 4 meshes, and I1 here will be equal to this independent current source, 4 milliampere. I2 will be equal with this Vx divided by 2K. And for mesh 3, this is a voltage source like negative 1K Ix plus 2K I3 minus I1 here plus 1K I3 minus I4. Then for mesh 4, we start from here, 1K I4 minus I3 plus 1K I4 minus I2 plus 12 volt. Then the controlling variable is we have to express Ix in terms of other variables within that circuit. So here Ix is in this one, in this branch. So this one is Ix equals to I4 minus I2. And Vx here is the voltage across this 2 kilo ohm resistor. And we can express it in terms of using Ohm's law. So Vx equals to 2 kilo ohm multiplied by I3 minus I1. So because of we use passive sign convention, okay? If any of you haven't really understood passive sign convention, please repeat the chapter 1, the chapter slide of chapter 1 and chapter 2 in the early weeks of this semester. Then we combine this equation, these 4 equations, and dividing by 1K, and then we obtain this equation. From here, we have 4 unknowns with 4 equation with 4 unknowns. So basically, we can use matrix. Yeah, we can also simply and so like this, put in the matrix form. So some of you still having difficulty in making it's still wrong, with the matrix. So please repeat again, review again the concept of matrix in the matrix product. Yeah, this is a matrix product. So basically, the matrix product here, this is equals to this coefficient multiplied by this plus this multiplied by this plus this multiplied by this plus this coefficient multiplied by this, or this one will be equal to I1. 0 times I2 is 0, 0 times I3 is 0, so 0 times I4 is 0, so I1 equals to 4, right? Then the second row will be I1 plus I2. Yeah, this is the unknown variable is this one, yeah, in the middle, yeah. So I1 plus I2 here, I2, sorry, negative I3 plus 0 times I4, so equals to 0. Yeah. Then 0 times I1 is 0. Then 1 times I2 is I2 plus 3 I3 negative 2 I4 equals to 8. Right? Then this one, the last row will be 0 times I1 equals 0. So this one is a negative I2, negative I3. Yeah. This times this one plus. Yeah. Then plus 2 times I4 equal to negative 12. So if you pay attention here, this is basically this for equation that we have obtained before. Okay, so be careful. You practice and practice how to convert this kind of multiple equation into a matrix format. Yeah, this is makes solving problems much easier, because after you put it into the matrix, then you can use MATLAB or Octave to solve and then obtain the value of I1, I2, I3, and I4. That's what I use to solve number 1 in the quiz 3. Only few of you, I look at your answer, use matrix method. Yeah, even then, some of you still is mistaken when converting this for the system of the equation into matrix format. While majority of you, when solving number 1, you solve using elimination and substitution. It's not a mistake, not an error is okay, but when the equation, the system of equation gets more complex and complicated, it's not that easy to solve using substitution and elimination. It is preferable or faster using matrix form. So please train and practice yourself how to convert from this system of equation into a matrix format. Okay. Okay, now clear. So from here, then it is very easy. Then we obtain. So here we convert this into put into the matrix format. Then after that, the voltage here is like this. Then we can obtain the answer using like this, or otherwise. So basically, this becomes, let's say, red, put it into red. Let's say this is a matrix A. This is the matrix I. Then equals to the matrix, the voltage matrix. So to obtain, this is the unknown one. So to obtain the unknown, what we do is the inverse of A multiplied by A. I then the inverse of A also, both sides of the equation we multiplied with the inverse of matrix A, like this. Okay, because this become an identity matrix. Remember what identity matrix? So this become I equals to A minus 1 B. You can use this one, but I would advise rather to use this format. Yeah, usually I try to use this when the value is not correct. So this one is better, using an inverse of the matrix. Okay. So, okay, then we continue further. Then this is an example of current with dependent sources. So we have here one single. So yeah, I think we have discussed this yesterday, and we can either choose of these two ways. We can choose. The first one is using mesh current. So loops which does not intersect to each other, does not engulf each other. While the second one, you use instead loop currents. So the first one is I1 on the first mesh, basically. The I2 loop currents engulf or enclose the first loop currents, yeah, in this method. So here, for example, with mesh 1, here we obtain this equation. With loop 1, here we obtain this equation. Then with mesh 2, here, this is the equation. With loop 2, this is the equation, yeah, from the outer loop. KVL, Kirchhoff voltage loop. Then we express the controlling variable here, Vx, in terms of the loop current. So here, Vx is the voltage across this 4 kilo ohm. If in this first model, then we express it as 4 kilo ohm times I1 negative I2. Well, in this case, only I1 flows through the 4 kilo ohms. That's why Vx equals 4K multiplied to I1. And then after that, we solve, after rearranging the terms, we obtain the same solution. V output equals to 9 volt. Yeah. Even though the I2 will be the same for both solution. However, I1 is different. Yeah. I1 in this model, we obtain 3 milliampere, while in this model, we obtain 1.5 milliampere. Okay, the selection of loop currents simplifies expression for Vx and computation of Vo. So here, when we choose this instead, then when we the expression for Vx is just simple. Vx equals 4K times I1. But if we choose mesh currents, then it becomes Vx equal to 4K times I1 minus I2. So this is easier because it only involves one variable. Okay, but it's up to you which one to choose. It's okay to choose to use the left side method. It's also okay. However, it's just a little bit more difficult. Okay, another example of dependent current source where the current source is not shared by the meshes. So we have here the current source here only involve I1. So we treat the dependent source as a conventional source. So equation for the meshes with current source. So this one, I1 equal to this current source, right? Because we treat it as an independent current source. So I1 equals to Vx divided by 2000. I2 here equals to this 2 milliampere, okay? Then the KVL is in this third mesh, yeah? Minus 3 here, plus I3 negative I1 times 2K, then plus 6K times I3. And then we express the controlling variable Vx. Where is Vx? Vx here is the voltage across the 4 kilo ohm resistor. So Vx equals to the 4k times I1 minus I2. Why I1? Yeah, according to the passive sign convention again. So we are asked for V output here. So then we only need I3 to calculate I3. After replacing an arrangement, the arrangement we obtain Vx here equals to 2 kilo times I1, and Vx also equals to 4k times I1 minus I2 here. Yeah, Vx here. Then I1 equals to 2 I1, and then 2 I2, we obtain I1 equals to 4 milliampere. So this Vx divided by 2000. Yeah? So based on this, yeah, we can obtain I1 value and I2 value. So using the the third loop mesh, we put into this equation, then we obtain I3 equal to 11 over 8 milliampere. So we can calculate the output 6k times I3, and we obtain 33 over 4 volt. Okay. Another example with a dependent dependent voltage source, current control voltage source. Use mesh analysis to find VO. So when you are doing a problem, you have to please read carefully the instruction. The instruction here is to use mesh analysis. So it means you cannot use any loop currents. Okay, your mesh analysis has to be, means the current have to be here and here. You cannot use the loop current that goes on the outer circle. Okay, similar, because in the quiz 3 I explicitly write use nodal analysis, but some of you, I would say, I do not say the name, still use loop analysis, right? It is supposed to use KVL to use, KCL, Kirchhoff current law, and use nodal analysis. So please read the instruction well. So first we draw the mesh current, I1 in this first mesh, and then I2 in the second mesh. Then we write the mesh equation. The first mesh for mesh 1 will be here -2 because it is voltage increase, negative kilo Ix, yeah, Ix, this one, the value of the voltage, plus 2 kilo ohm times the current I1 plus 4 kilo I1 negative I2, right? The current flowing through this 4 kilo ohm resistor. At mesh 2, negative I2, negative 12 from here, so we depart from here. Negative 12 plus 2k times I2 plus here 4k I2 minus I1, because the loop is in the I2 here. Then we write the control variable. Ix is the current flowing through the second mesh, basically. So it means that Ix equals to I2. Okay. So then we replace and rearrange. So we obtain 6k I1 minus 6k I2 minus equals to 0, and then minus 4k I1 plus 6k I2 equals to 12. We solve for I2, so we obtain, so how? We multiplied this with first equation with 2 and multiply the second equation with 3, with a factor of 3. So then we obtain 2k I2 equals to 12. I2 equals to 6 milliampere. From there, I2 basically is the Ix, right? The V output will be the current I2 times the 2 kilo ohm. 6 milliampere times 2 kilo ohm equals to 12 volt. Okay, in the following we shall solve using loop analysis two circuit that had previously been solved using node analysis. So this is one of the circuit. We recap first the node analysis approach, then we solve using loop analysis. Okay, so this is the circuit that once I think we have done this in the node analysis discussion. So here we use the super node, right? Remember, using super node, and then the other node are written here. So V4 is 4 volt, basically this one. And basically, yeah, one thing to note is when in node analysis, you usually to find the reference volt, the reference node is the node which has the largest amount of branches. Okay, so in this case, that's why the bottom part is become the reference node. Okay, Why I'm saying this? Because in the quiz 3 as well, to solve number 3, some of you redraw the circuit and then make the reference nodes some node which does not have the most number of branches. Yes, you can solve using that way still, but you just make your life more difficult, yeah, if you do it like that. Okay, that is just a rule of thumb. Is you choose the reference node as the reference node, which is the node which has the largest amount of branches. Okay, at the supernode, V1 minus V2 equals to 2 Vx, right? And then, so we write down, this is using node analysis, yeah? So here, negative 2 milliampere, because this current is flowing into the supernode, plus V2 divided by 1K, so this part, yeah? Plus V2 minus V3 divided by 1K, plus V1 negative V3 divided by 1K, and then plus V1 negative V4 negative 4 volt divided by 1K. So pay attention that even the supernode here, basically this is still considered as that part of the supernode, yeah, this part, this, because it is just drawn spread, but basically they are still the part of that supernode. So from here then at V3, as is written here, then the controlling variable Vx is the voltage across this 1 kilo ohm, basically is the same as V2. Yeah, then we solve the equation by multiplying with 1K, all this equation. Then we obtain this system of equation having 3 equation with 3 unknown, V1, Vx, and V3. With the variable of interest, V output is here, yeah, which is V1 negative V3. Okay. Okay, then clear the drawing. If we use loop analysis instead, we can choose first meshes. So first mesh, the first mesh here, the second mesh here, third mesh here, and then we can have a general loop to avoid this current source, because this current source, if we choose a mesh on this rightmost loop, yeah, then we have this current source which is set by these two loops, yeah, which is usually we don't want that. So remember the session yesterday. So we will meet another loop which does not share that current source. Just in this case will be this I4, another loop containing the containing I2 and I3. Okay, so writing the loop equation at loop 1, I1 equals to 2 milliampere. Loop 3 is here. This is, we have already this 2 milliampere, right? So loop 3 will be I3 equals to negative 2 milliampere, because the 2 milliampere is upward while I3 is clockwise. At loop 2, negative 2 Vx, so using Kirchhoff voltage law plus 1K times I2, then plus 1K times I2 negative I3. At the loop 4 here, the 4 volt, so coming from here, from this point, 4 volt, then times 1K here, multiply times I4 plus I3, yeah, I3 is the same direction, negative I1. So then here at this point, negative 2 Vx, because this is voltage increase, then plus 1 kilo ohm multiplied to I4. Okay, so from here, the control variable is Vx. We need Vx equals to the voltage across this 1 kilo ohm, which is basically the here. Yeah, the Vx is mentioned here. So 2K. After that, then we solve the equation. So we can replace the Vx here, yeah, equals to 1K times I1 minus I3 minus I4. So we place each of the Vx in the previous equation with the this. So from there we obtain these two equation, having two unknown I2 and I4, and then we obtain I2 equals 1 milliampere, I4 2 milliampere. The variable of interest that is asked is V output here. So V output is calculated using 1 kilo ohm times I2, right? So we have obtained I2, so 1K times 2 milliampere is 2 volt. The output is 2 volt. So this is another example. Basically, due to the time, I will just skip this. or I just give a little bit quick discussion. So negative V1 equals C. Yeah, this is using node analysis. Yeah, basically similar like before. Okay. Then this is if you use mesh analysis. Select the mesh current like this, easier. So that do we have a current source which is shared by two mesh? No, we don't have. So it is okay. So we don't need to choose a loop current which is engulfing other mesh current or loop currents. Yeah? So loop one, 1K times I1 here, 1K times I1 negative I2 plus 1K I1 negative I4. In loop 2 here, 1K multiplied by I2 minus I1 plus or no, negative 6 volt, yeah, because it is voltage increase in the direction of the loop, plus 1K I2 minus I5. Loop 3 is here, I3 equals to, this is a current source, that's why I3 equals to 2Ix. And loop 4 is here, negative 12 volt plus 1K, I4 minus I1 plus 2Vx. Loop 5, it is here, 1K I5 minus I2 plus 1K I5 minus I6 minus 2Vx. And finally, loop 6, yeah, 1K times I6 minus I5 plus 1K I6, this part, yeah, and then plus 1K I6 minus I5, and this one I6 minus I3. Okay. The controlling variable Vx is the voltage across this 1 kilo ohm, or 1K times I1, negative, yeah, negative, because this is it is contrary to the passive sign convention. That's why we have to put negative here. And Ix is the current flowing through this branch, so it means Ix equals to I5 minus I6. So we have eight equations with 8 unknowns. So here, usually it will be easier later if you put it in matrix form, yeah, rather than if you solve it one by one using elimination or substitution, then it will take longer time. Okay, if you rearrange the terms, I1 with I1 coefficient, I2 with I2 coefficient, I3 with I3, and I4 with I4 until I5 or I6, then you put it in row and column of the matrix. Okay, so that is for the loop analysis. I think we finished, and after that there is application and design, but we are running out of time for today. Yeah, application and design only have 3 slides, so let's just review it quickly. Okay, so here we have manual speed control for DC motor. So this is the DC motor. We need to drive the DC motor with the correct power. Okay, so the speed is proportional to the applied voltage VM. Yeah, VM is, where is it? Here. Yeah, this is the VM. Yeah, voltage across the DC motor, and that is also according to the current here. And we have potentiometer here to tune the voltage, yeah, from this 5-volt source. Yeah, this is a voltage divider. Remember, voltage divider circuit. Yeah, in I think the early chapters. So the arm in a potentiometer is movable, so it allows to change the value of R1 and R2, but the sum will still be constant. R1 and R2 will still be a R, the total R, which is RPO. So R2 here equals to the alpha times the R potential, R potential in the term. So this is a battery. So when we have the assumption that no current is being drawn into this power amplifier, yeah, so it means it is a perfectly voltage divider. The impedance here is very high, so that's why no current is being drawn towards this DC driver. So the potentiometer is not affected by the connection to this amplifier. The circuit diagram is like this if we model it into a circuit. So we have here the voltage, yeah, of the speed. So here we have the voltage across the motor is 4 times the V speed here. This is a power amplifier model. This is a voltage dependent voltage source to model this power amplifier. So the omega RVM equals to the constant times the VM, the voltage across that DC motor, which is equals to 4 km times the voltage speed here at the power supply part. So the omega RPM equals to 4 km the V battery times alpha. Yeah, this is from this part. Yeah. An 8-volt source is to be used in conjunction with 2 standard resistors to design a voltage divider. Yeah, the voltage will output 5 volt when connected to a 100 microampere load, while keeping the consumed power as low as possible. This is to minimize the error between the actual output and the required 5 volts. So this is the load, 100 microampere load, drawing the current 100 microampere load. So using node analysis, yeah, at this point, I/O, yeah, I/O, current out, plus V output, this is V output divided by R2, plus V output negative Vs divided by R1, equal to 0. So I output is 100 microampere, V output here is 5 volt, because this is 5 volt here found from the question. Minimize the error between the actual output and the required 5 volts. Vs is 8 volt. Now we are asked to determine R1 and R2. So for example, if R1 equals to 3R2 divided by 5 plus I output times R2, so R2 equals to 5 divided by, this is the design equation, 3 over R1 negative IO. So the power is made to be as low as possible. This is the power is from the R2, V output divided by R2, and power at the R1 is Vs negative V output here, the voltage across R1 squared divided by R1. So then it means to make the power as small as possible, we have to make the resistor value high. So, but why not having very large? So we have to use trial and error, pick the highest possible R1 value, and then we determine the R2 to analyze the resulting circuit. Let's, for example, pick R1 to be 27 kilo. So using this design equation, we obtain R2 to be 450 kilo. So this is closest R2 in the market that we can purchase is 430 kilo ohm. So from here, this is the output from determined from here equals to this equation. So we obtain then the output to be 4.98 volt. Okay, so the output here 498 volt from the 8 volt. Okay, this one example. Usually, when in the design, you have, after you calculate, then you have to adjust it with the values of the resistor, whatever that is available in the market. For example, this is the value in the market, yeah, the values of resistor, standard resistor value. So with that, I would like to conclude for loop analysis discussion.